Now, regarding the anchors, we will check the shear and moment capacity again, along with the cable bearing on to the anchor block. And remember from the component analysis section on anchor analysis, we approximate the anchor block as a rectangular section resisting the cable forces perpendicular to the load. And we can set up the anchor block perpendicular to the load, the section resisting the cable forces. And we can set up our equations for moment capacity using strain compatibility, and our equations for shear capacity are also discussed in the component analysis section. This depends on the area of the concrete and shear, along with the size and the spacing of the stirrups. Once again, none of these derivations I'm going to go through again. These equations should look familiar from the component analysis section. I don't want to waste time going through that again. What we're going to talk about is what variables are going to change and what we're going to be comparing our capacity and our demand, how we're going to be comparing our capacity and our demand. So once again, we have our ultimate moment and our ultimate shear. That's just going to be phi times the nominal moment or shear, which we use a phi of 0.9 for tension-controlled section in flexural capacity, and we use a value of 0.75 phi for a section in shear. Whereas that ultimate moment is going to be 1.4 times the dead load moment, or 1.4 times the dead load shear, which we can then just plug in the equations we derived in an earlier section where I showed those moment and shear diagrams to get our full equation for moment and for shear. That is going to be the demand. Once again, everything should remain the same except for our variable A in the flexural capacity equation and our variable F prime C for shear in the concrete capacity portion of the shear capacity equation. For flexure, like the tower checks, the depth of the concrete compression block will increase, having to engage more concrete in compression to make up for the fact that it is weaker. We can plug in our new F prime C as a function of T value based on how many days we want to load our anchor. And we can check that our section capacity is sufficient under both the hoisting and design load conditions or dead load conditions. We can also plug that new F prime C as a function of T value into our new sectional shear capacity, VC, and that will update our VN value, and we can double check that we're still going to have sufficient shear capacity at the amount of days we'll be loading our anchor. The final condition we also want to check again is bearing. The beam may have sufficient strength as a whole, but we also want to confirm that the cable point loads won't overcome the bearing strength of the concrete at that time and pull out of the anchor and cause damage. Once again, the loads are going to be less than they are during the full loading when we did this check in the previous analyses, but the strength of the concrete is also going to be less. So we want to redo this entire check to make sure that it is all sufficient. So for the cable bearing, we'll use the same service load and factor demand of 1.4 dead load. That's that BU value. Except we will be looking at a force of a single cable again. So we'll follow the procedure from our anchor analysis, adjusting the bearing capacity, Bn, to reflect our lower compressive strength, F prime C, as a function of T. And as a reminder, we can get that single cable force using the PT back hand value divided by 2, because the largest force is coming from the handrail cables. And then also as a reminder, the bearing area A is approximated using the diameter of the cable loop, not the full D effective, because this would actually inflate our distance. So we can call this dimension D effective prime. And I've made a little drawing here of how we have this circular cable with a diameter of the loop D effective prime, and how that is being modeled as a kind of rectangular bearing surface conservatively to calculate our both our force and our demand and our bearing capacity. And that bearing area can be adjusted up to 2 times its initial area based on ACI 318, and because there is space for that, there is concrete above and below for that bearing area to dissipate force in either direction, we can adjust it time by a factor of 2. So now that we've completed these checks, we can add a series of checks and flags that will trigger us to review the concrete strength calcs further if the demand exceeds capacity. If you're building this into a design tool, I would recommend building out all these equations and checks and making a function of the variable t, of time and days, so that when you're on site, or if you're calculating how long it's going to take until you can hoist, or you can high hoist, or you can set sag, or you can begin decking, or how much material you need to be built on your abutments before you can do these things, it all can be a function of time. So once you have all of your information about your bridge input into your design tool, you can adjust that variable t and figure out, okay, we need 3 days or 4 days or 7 days and before we can officially begin hoisting our cables, or we can officially begin decking in order to avoid any early failures.